Good afternoon, sir. Sir, Dr. Balamurugan, sir. Sir, can you hear us?
Yes, ma'am.
Okay, sir.
Yes.
Sir, can we start the session?
Yes, I can hear, ma'am.
Okay, sir. Good afternoon, all. To continue with, now I would like to invite S. Niveta from 3rd BSc Physics to the stage, who will share a few words about our speaker, Dr. Balamurugan.
Good afternoon, everyone. It's my honor to welcome Dr. Balamurugan Jayaraman, who is a distinguished research assistant professor at the Korea Advanced Institute of Science and Technology, KAIST, within the Department of Material Science and Engineering. He also holds a key research role at the National Creative Research Initiative Center for Multidimensional Director Nanoscale Assembly, with a Ph.D. in Chemistry from Anna University, India. His research focuses on energy storage and conversion technologies, including supercapacitors, metal-ion batteries, and metal air batteries. Additionally, he is working on innovative biosensors for highly sensitive and durable detection of biomolecules from the human body. Dr. Balamurugan has made significant contributions to the field of nanomaterials, specializing in the design and development of flexible, high-performance 3D nano architectures and single-atom catalysts for energy technologies. His research covers advanced energy storage solutions like solid-state energy storage devices and rechargeable metal air batteries, alongside sustainable technologies such as water splitting and fuel cells. He has held prominent research fellowships, including the Korea Research Fellowship, and has contributed extensively to academic literatures with over 67 published articles, garnering more than 5,800 citations. His scholarly work includes publications in leading journals such as Advanced Materials, Chemical Engineering Journal, and ACS, Applied Materials and Interfaces, where he has served as both first author and corresponding author. He has filed several patents related to 3D nanostructures for energy storage and water electrolysis. Dr. Balamurugan's future research ambitions include advancing the field of flexible biosensors for medical applications and new energy storage materials. Thank you.
Thank you, Niveta. Success is not final. Failure is not fatal. It's the courage to continue. Now I welcome Dr. Balamurugan Jayaraman, Research Assistant Professor, Korea Advanced Institute of Science and Technology, to deliver the lecture. Over to you, sir.
Ma'am, can you see the slides?
Sir, we can see you, sir.
Okay, ma'am. Okay. So, thank you, ma'am. Thank you for giving the great opportunity to deliver my talk in the international conference. So, especially special thanks to Professor Grija, ma'am, and thanks for the organizing committee, and thanks on all present here. So, can I start to my talk, ma'am?
Yes, sir, you can start. Yes, sir, you can start.
Okay, ma'am. So, good evening to all. So, today I'm going to discuss about the single atom catalyst and the role of single atom catalyst for energy applications. So, the people know very well. Previously, people making bulk nanomaterials and they transform from the bulk nanomaterial to the small size nanomaterials, and then they move to single atom. Because single atom is nothing but the single metal or single whatever we are using single atoms. It helpful for the catalytic towards the energy application like energy storage and energy conversion applications. So I am going to discuss about the introductions, which includes the single atom synthesis protocol and what are the properties of single atom and applications, especially energy storage and energy conversion applications, experimental discussion about the synthesis methodology, results and discussion. We are going to discuss about the material characterization analysis and finally
Excuse me, sir.
how it will apply for energy storage and energy conversion applications. And I'm going to conclude the
Excuse me,
session with the research outputs. So how it will be helpful for the energy storage and conversion applications. So you people know very well different type of energy and energy storage and energy conversion technology.
Excuse me, sir, we are not able to see your presentation.
Our single atom catalyst used for different type of applications like water splitting, as well as catalysis application like hydrogen ablution, oxygen ablution, and reduction reactor. And they are using catalyst for the solar cell and fuel cells. As well as they are used for recently capacitors and batteries. So finally, the single atom catalyst used for the biosensing.
Sir, Dr. Balamurugan, sir.
Yes, ma'am.
Sir, we cannot able to see any slides, sir. Are you sharing any slides?
So you cannot be able to see the slide?
No, sir.
Oh, no, I asked you that slide. Maybe it is shared. Okay. Now, ma'am?
No, sir. Only your camera is visible.
Oh, really? This problem will come issue. Okay, ma'am, just 1 minute. I will check. Actually, I have to stop sharing. But it's showing. But I don't know.
Sir, now your screen is visible, sir.
Now, okay, ma'am?
Okay, sir.
Now, can you see the slide, ma'am?
Yes, sir.
Okay, ma'am, thank you. Okay. So now I'm again starting. The title is the next generation energy storage solutions. So energy storage and conversion applications, how the single atom is applicable for energy storage and conversion application. So introduction, I already discussed about the introduction of the single atom and how it will be work for energy storage and conversion application. Experimental discussion, experimental section and dissert discussions, we are going to discuss about the single atom, how applied for energy storage and energy conversion, and finally I'm going to conclude. So the people know very well different types of energy storage and conversion application is available, especially catalysis, hydrogen ablation and oxygen ablation reactions, especially it used for the water spreading applications, and oxygen reduction reaction and oxygen ablation reaction it applied for fuel cell application, and we also going for capacitors and battery. And finally, the single atom based catalyst is used for the sensor and biosensor, especially biosensors to detect the many ingredients in our body, especially hydrogen peroxides and glucose. Hydrogen peroxides differentiate with a normal patient to the cancer patient, we can detect from the biosensing. So you can see surface free energy is one of the important key factors for the research aspects. When the bulk atom converted to single atoms, the surface free energy is enhanced. As well as specific activity also enhanced. People moved from the bulk to nano to sub-nano, like quantum dots, and finally they go to the single atoms. Because when minimizing the metal size like a single atom, the specific activity will be increased. And the material engineering, they first fabricating 3D type materials, and finally they go for 2D materials and decorated with the nanoparticles over the 2D materials, and finally the people move to single atoms. So you can clearly observe from how coming from the bulk atom to single atom, usually single atom have high advantages towards the energy application. Therefore, we are going for the new trend for single atom catalyst. And the catalyst developments, you can see previously noble metal based catalysts people are using, and in order to reduce the cost of noble metal, they moved with the noble metal with non-noble metal alloys. And they are mixing together, and finally they go for coastal material, and finally they go for non-precious material. And whenever go for non-precious material, even though they can't achieve the high performance, therefore move to single atom catalyst. So in order to go for nanomaterials to the single atom, the specific activity is enhanced. Therefore, the people are trying to make single atom. But even though single atom is a new type of materials, but nowadays the people trend is single atom, but there is limited facility to analyzation. Especially the single atom analysis by Zan's analysis, it limited availability in all over the world. In overall Korea also there is only one place, the Bogang Center, they have the analysis center for Zan's analysis, and in India also one or two places it is available. Therefore people try to go for single atom catalyst to confirmation of single atom catalyst from the nanoparticles. You can see in our studies, we first fabricate some, mob-based material. Why people are moving for mob-based material compared to other material? Mob-based material has a high surface area. Therefore, we have chosen a mob-based material for temperating agents to get the single atom decorated, the carbon supports materials. Especially when go for mob-based material, it has high porous networks. So we are fabricating highly porous networks to penetrate the electrolytes and ion transportation, plus the kinetics will be enhanced. So in order to avoid the kinetics issue, people are going for the porous material with the single atom catalyst. Another one thing, there is the issue for single atom loading, and limited quantity of single atom only we can load separate atomers. Then when increasing the loading, then lot of cluster formation as well as it make particles. So these kind of particles may be reduced activity again. Therefore, certain amount of single atom only we can load, around 2.5 or 3%. When increasing the loading, then the single atom loading, then it may be make the cluster formations. Therefore, in order to avoid, therefore we are going for high surface reactive material. That material may be helpful to enhance the electroactive size. So finally, we are fabricating the flexible devices, and that devices may be getting the high energy density and power density. So after fabricating the materials, we have to do some analyzations like morphological investigations. You can see morphological investigation, especially STM at the high magnifications around 1 nanometers or 0.5 nanometer or 2 nanometers, then only we can see the single atom cut. You can see we have round up some single atom, yes. Another thing I told you, the analyzation from a limited facility of ZANS and XAPS analysis. From this analysis only we can find this is single atom or this is nanoparticles. So we can differentiate nanoparticle from single atom from this analysis, but it is limited facility in all over the world. And after confirmation of the material, we are doing some theoretical performances to predict the optimal catalyst. So how it performed, so which optimal catalyst may be helpful for the energy storage to give the high energy density power density. Finally, after confirmation the theoretical test like oxygen reduction as well as oxygen revolution and hydrogen evolution reactions, and finally we need to fabricate the device. That fabricated devices may be helpful for the real world energy applications like battery, and it may be energy storage devices, and it may be helpful for different type of battery technology in aeroplane or whatever we are using in the commercial aspects. And what is the single atom? So why we are using for single atom for different energy applications, especially capacitors, battery, and especially energy metal ion or metal air battery like lithium ion or lithium air battery. And finally, they are also used in energy conversion device like solar cells, fuel cells, and water splitting. So people know very well water splitting is one of the techniques to produce the hydrogens in the very facile methods. And this one may be helpful to make the highly flexible energy storage device in modern electronics devices. So why we are going for the modern electronic device, especially the flexible energy storage devices? In order to use the liquid-based electrolytes, you cannot be able to use in different atmospheres. For example, India, there is no problems, but India has a high temperature, more than 35 degrees centigrade. But in case of the other country like Canada or Europe or USA or Korea, even Korea or whatever the country, they are going for lower temperatures around -30 to -35 degree. When they go for lower temperatures, the electrolyte is solidified. Then the ion transportation will be a big issue. Therefore, we are going to get the solid-based electrolytes. When going for solid-based electrolytes, we can go for flexible energy storage devices. Then we can use for the lower temperature like below 0 degree centigrade, for example, -25 or -20 degrees centigrade. There is no issue for the ion transportations. So metal air battery, you can see when the metal used as the battery like a anode, this is anode part, this is cathode part, yes. So when the metal, for example, zinc or lithium or whatever the metal, ion or any other metal, that metal we called metal air battery like a lithium air or zinc air or iron air battery or magnesium air battery. So in our case, the metal, there is not much issue, but even though there is dendrite formation will be issue. But even though when go for the air electrodes like air cathode material, there is lot of issue, especially the transition metal, the noble metal people are using like a platinum based catalyst or iridium or ruthenium based catalyst. So in order to reduce the cost, we have to make the low cost material. That material should be stable in air media, in the air atmospheric media during the charge discharge process. That is our aim to develop the material. That material should be highly stable and highly, highly performable or high kinetics towards the OR or OER performance, like oxygen reduction and oxygen evolution reactions. You can see different type of energy storage device already available, like lead battery or nickel cadmium or nickel MH battery or lithium ion battery. But when go for the specific energy, because specific energy is challenging for the research community. So when go for the specific energy compared to the commercial available lithium battery, lithium air battery or zinc air battery is one of the key challenging. So we have moved to the high energy, high specific energy as well as theoretical as well as practical energy. Therefore, we are moving to the lithium air as well as zinc air battery. So when go for lithium air battery, there is a lot of issue because lithium air battery, they are using non-aqueous based electrolytes. So when used in the commercial aspects, sometimes it may be as the authorities issue. Another one, the safety issue, especially Similarly, the non-aqueous electrolyte sometimes may be making the flammable. Yes, therefore we are moving for zinc air battery. But when going for the volumetric energy density, zinc air is higher than the even lithium air battery, and it may be more safer one compared to the lithium air battery. You can see, I told different type of the material, platinum-based material, especially used for ORR, iridium-based material used for OER. But in case of both ORR, OER happen in the air electrodes, that should be bifunctional activity. Therefore, we need to develop the air cathode materials. There is a lot of issue, like currently there is a lot of issues, air electrodes, metal electrode and electrolytes. But we need to design the material. That material designing should be enhance the performance. It may be boost the efficiency, like coulombic efficiency, cycling stability, and it may be helpful to the commercial aspects applications for the different type of gadgets, and maybe used for the electric vehicles, and maybe it may be comparable for the commercial available energy storage devices. So these are the drawbacks. I told that highly cost materials, and maybe we need to overcome this material. We have make the new strategy, that make that strategy like a single atom decorator strategy. That strategy may be enhance the cycling life, and finally that strategy may be helpful to develop the electric vehicles, car, mobile or computer, smart mobile or computers, maybe gadgets, maybe it may be used as an energy storage systems like a battery. So it may be currently available or commercial aspects for different type of energy storage devices. Especially nowadays people are going for flexible energy storage devices rather than stable aqueous-based energy storage devices. So recently we have developed a single atom based, especially molybdenum single atom based materials in case of the nitrogen doped carbon frameworks, because nitrogen doped carbon frameworks may be helpful for enhanced conductivity, but when the molybdenum anchoring on the carbon substrate, that nitrogen may be highly, bonded with the molybdenum single atoms. You can see there is the red color one is molybdenum single atom, it bonded with the nitrogens, because nitrogen and carbon bonded. But when we are making this kind of shell molecules, we are doing pyrolysis process. That time we are instantly taking the lot of single atom over the shell molecules of, because carbon shell, nitrogen doped carbon shells, and that carbon shell may be act as the active sites for the energy storage device like a metal air battery. You can see when it kind of core shell molecules, the core has the vanadium, molybdenum, nitrate core that may be enhance the conductivity. Then the molybdenum single atom may be helpful for the anchoring sites. Maybe the people know very well, DFT calculation people know which one is active sites we have to prove, but when we are calculating the active sites, molybdenum may be helpful for the highly active compared to the vanadium, then may be helpful for the energy, especially air electrodes. It may be helpful for both the bifunctional activity like ORR and OER. So I am going to explain in the details. So after fabricating the materials, we have to do the pyrolysis. After fabricating material, we have to confirm by the morphological analysis. I am doing the SEM analysis. You know very well, when the particles may be decorated with the graphene layer, but lot of aggregation happen. But in case when we are fabricating the materials with like quantum dots and surrounded by shell, there is not aggregation happen. Lot of porosity maintained, and it has the high surface area. And you can see there is not much particle is observed, maybe it observed from the SAD patterns. But in case the particle observations, maybe SAD patterns have the highly crystallinity, yes. But when we are checking the high magnification image of the core, it may be show the highly crystalline nature of the vanadium, molybdenum, nitrate phase, and the shell has large number of single atoms. You can see molybdenum I have rounded, and the color mapping is really says the uniform distribution of molybdenum in the core as well as shell. But in case of the molybdenum, the core and the shell, but in case of vanadium, it only present in the core but not present in the shell. But nitrogen is also presented because nitrogen intensity very high in the core compared to the shell of the system. And finally, after confirmation of the materials, we have to go for the structural investigations. I told you the structural investigations clearly says the molybdenum bonded with the pyrulic states compared to the other state of pyridinic or graphitic states. So pyrulic molybdenum is rather than the pyridinic molybdenum in this case, and the molybdenum has a different phase like a 4+, 6+, and the nitrate phase also available. It may be confirmed by the molybdenum nitrogen bonding, and I previously told that the SANS analysis is one of the important techniques to predict the molybdenum bonded nature, because local structure predicted from the SANS and EXF analysis. You can see the R value below 2 usually told that metal with anion bonding like nitrogen or oxygen bonding. But when go for after metal bonding, you can see molybdenum bonding. So when they go for the lower R value, even though the lower R value has different, range. For example, molybdenum nitrogen bonding one phase, molybdenum oxygen bonding somely shifted, and the molybdenum sulfur bonding little more shifted. Maybe the local structure may be performed by this analysis. So after confirmation by the analysis, we can say molybdenum single atom is decorated over the nanosheets. And I also showed the fitting data. Molybdenum bonded with 3 nitrogen and 1 carbon. And vanadium, you can see there is no vanadium nitrogen single atom is observed. Only vanadium nitrogen bond is maybe getting from the vanadium nitride, and the vanadium bond is majority. Therefore, vanadium there is not a single atom, but in case of molybdenum only single atom in this case, but vanadium in the core of the nanoparticles. And finally, WT-EXF analysis also clearly sees the R value is lower than 2, and in case of the optimal catalyst compared to the foil. Foil has the metal bonding and similar observations are observed for the vanadium case. And after confirmation of the structural and morphological investigation, we are doing the 3-electrode test in the ORR and OER test. This is ORR. When we are doing the ORR analysis, we have to convert into the RHG value. The potential first we performed in the HG because we are using KOH media. When we are using the acidic media, we have to use AgCl electrodes. But when we are using the HG electrodes or AgCl, we have to convert into RHG value. After converting RHG value, we have to see higher potential value, because we can call this area onset potential, this off place, because in middle of the place we called it the off-wave potential. The off-wave potential towards the positive region is the higher kinetics as well as the high performance of ORR compared to the other catalysts. So in order to compare the ORR catalyst, we have to prove the commercial platinum carbon. So it is better than commercial platinum or it is poorer than platinum. But in case of our optimal catalyst, higher performance than platinum, and we also tested in the different rotation speeds. When increasing rotation speed from the 400 to 3,200, then there is, the current density drastically increased. From the curve, we calculate the KL plots. From the KL plot, we proved that this number of electron transport mechanism is around 4. So when the case is around 4, then we can claim this is obey with the ORR performance. If suppose we get 2 electron transport mechanisms, rather than ORR, it happens like a hydrogen peroxide evolutions. When hydrogen peroxide evolution happens, the electrode degrades slowly. Therefore, we need to prevent from the hydrogen peroxide liberations. Therefore, we have to make the perfect electrode for ORR reactions. So we also perform the durability test and comparing with the platinum carbon. Platinum carbon is the current density drastically changed after a few hours, but our material is highly stable when rotating at 1600 rpm. And we also do the OER performances. In case of the OER, we have to see the OR potential around 10. Why we are checking the around 10? Because the commercial or already reported material always checking with the 10 milliamperes. So therefore, we have to check the 10 milliampere with the low value. That's called lower OR potentials. So in case of optimal catalyst, getting the lower OR potential even compared to the iridium oxides. In case of the ORR, we have to use platinum carbon. In case of OER, we have to use commercial iridium oxide or ruthenium oxides. But we have to compare ruthenium oxides. Our material has the higher performance in basic media. And we also check the kinetics. I told you kinetics is also one of the important tasks, but the TOEFL plots clearly says the lower kinetics values is the higher kinetics, lower TOEFL value is the higher kinetics for both the OER and the HER, OER and the ORR value. And finally, the bifunctional activity is also very close compared to the other comparative material. And we also proved by DFT calculations, it may be the free energy value very close the value, then oxygen absorption and the desorption very fast during the ORR and OER performances. This is the mechanism for the oxygen absorption mechanisms, because OH, OO and OH absorption and desorption is very important during the ORR and OER performances. And after confirming the 3 electrode test, we have to go for the device. So when go for device, we need to check the power density as well as the energy density. Yes, but when go for the power density test, our catalyst we can use for bifunctional of our catalyst. But in case of the commercial one, because commercial one we have to use for overall platinum carbon, iridium is OER. Yes, then we have to mix 1:1 ratio when go for the bifunctional OER activities. Then the performance of our catalyst more than 2 times higher, around 2 times higher, maybe 1.8 times higher than the commercial one. Then we can claim that our catalyst giving the higher power density, peak power density compared to even commercial or already reported materials. And we also show the practical applicability when growing the LED with the series connected devices. Then we can see, you can see the KAIST LED is glowing for a long time. Then we can say our material give the practical applicability towards the glowing LED. And the specific capacity and the energy density also even higher than the commercial catalyst. And the one important task for the durability issue. Yes, but when go for the battery devices in the long-term durability around more than 600 hours, you can see this down part is ORR part and the upper part is OER. But in case of our commercial catalyst, the cell voltage is maintained. But the commercial catalyst, both cell to voltage is lost. Yes, in case of the commercial, there I also showed here the zoomed view around 180 hours. But in case our catalyst giving the higher, higher time, more durability. And we also do, this is the liquid based devices. And in the commercial aspect, I am also fabricating the flexible energy storage devices and by bended with the different angles. You can see 0 degree, 45 degree, 90, 180 degree. There is no distortion happen both the cell voltage for upper one and lower one. And we also tested for commercial aspect for different country in temperature tolerance ability. Yes, when I used lower temperature around -20 degree and around 80 degree, but 80 degree the performance increased, but when go for -20 degree, even the cell is maintained the voltage not below 1 degree, 1 cell voltage. Yes, then we can say from the study conclude the catalyst giving the high peak power density, high energy density, and as well as it may be highly practical applicability. And we also fabricated dual electrodes, dual atom catalyst. Previously, I told only single atom catalyst, but now 2 different atoms. Like I checked one atoms like iron, Fe, and I also modified with another metal atoms with the nitrogen bonders. You can see the blue one is nitrogen, and I changed different metal atoms. You know very well the periodic table first row, second row, third row has different behavior. The first row material is very cheaper, even though the behavior is different compared to second row and the third row material. In case of the first row, usually more stable in alkaline media or it not stable in acidic media, but especially iron is more stable in acidic as well as alkaline media. Therefore, I choose iron and I change the different metal. But when I change the metal with the iron combination, you can see I am getting the iron rhodium combination is far better than other catalysts in both acidic as well as alkaline media. So you can see the dot, the high bright dot is the rhodium because the atomic size is big. The small bright dot is rhodium, iron. So in case of iron and rhodium, the distance between these both atoms may be matched with our theoretical calculation of 0.257 nanometers. Then you can see that high bright dot and low bright dots we can also show. In case of the TM analysis, there is no crystalline peak observed. From the studies, we can conclude that there is no particle also observed. So from the studies, we can conclude that our material successfully synthesized without nanoparticles, only single atom decorated throughout the graphitic networks. So when I do the synthesis, I also use this kind of material for templating to remove the PS dot molecules, to remove the template. After removing the template, I get the highly porous networks. So after making the material, I also studied with the conformation studies, exams, and EXF analysis. I previously told that the below 2 R value, we called that metal with the carbon as a metal with the carbon or metal with the anion, like nitrogen or carbon or sulfur bonding. So in case of our optimal catalyst, this bonding is observed, and another peak also getting that because near another one metal is present as like rhodium and iron. So in case of this is iron, and in this case of this one is rhodium, because we have to check local structure from the iron KH and the rhodium KH. We also do the oxidation states, because when the metallic states, usually the pink one is metallic state, is zero oxidation states. When the metal oxidation states increased, then it's also going to the positive directions. So further we also comparing with the single atom and the dual atoms. You can see dual atom getting the another additional peaks, but in case of single atom there is no. Then we maybe conclude that rhodium is nearly bonded with the iron, but there is not much affected by the metal nanoparticles. And rhodium also getting similar observation like iron. Then we also studied and confirmed this material may be highly dual atoms, dual single atom, there is no metal particle observed. And like previous studies, I told the catalytic activity and the kinetics also, we also proved that the highly kinetic lower value of TEFL may be high kinetic towards the aura, and the durability when comparing to the commercial catalyst may be highly stable. And we also check alkaline media like 1 molar KOH and acidic media like sulfuric acid media like 1 molar sulfuric acid media. So when we check both alkaline and acidic media, it may be getting the higher onset and offset potential. But we also studied the OER performances. Then OER performances clearly says our optimal catalyst for rhodium ion is better than other combinations like iron nickel, iron cobalt, or iron iridium, or iron platinum, even commercial catalysts. So from the studies we conclude that the iron rhodium is the better catalyst even compared to the other ratio of the catalyst. So we also check the peak power density. It may be around 2.5 times or 3 times higher than the commercial one. And durability, previously I told 600 hours, but in case of dual atom we get around 1600 hours more stable. But when we go for the commercial catalyst, so other comparative catalyst, you can see the peak power density compared to very high, and the reversibility. Usually, when go for lower current to higher current, because usually the battery need to go high current because rate capability is very important. When going for the higher current density, our material, you can see the red one is highly reversible. There is not much less than 1 cell voltage, but in case of a commercial one, it may be lost around 0.8 voltage. So we also do the durability, different bending angle. You can, I showed the figures in the different bending angles in the live video, live photo, and the temperature tolerance ability also highly performance. And from the studies also we can do single atom and dual atom catalyst. Dual single atom catalyst is the better for the energy storage device, energy conversion devices like a zinc air battery. And we also do some additional studies for like material developments and used for metal air battery, or this is additional studies, different type of material we have developed, and I also used for the bifunctional and the trifunctional applications. So these are the DFT calculations, and we also do different type of metal air batteries. And you can see, so when conducting the metal air battery, how it will work to split the waters. So when we are using the electrodes, one is hydrogen abolition, another one electrode is the oxygen abolition electrodes. So this is the bifunctional, yes. So when connected with our device, it may be, split the water molecules. So during, the splitting happens, hydrogen one side is abolition and another one is oxygen abolition happens. So we have developed a lot of materials and we also performed for the metal air batteries. So next topic is I'm going to discuss about the lithium ion battery. So lithium ion battery, you know very well about lithium ion battery. Even though the lithium ion battery is limitation, certain level of energy storage density, therefore people are nowadays going for lithium sulfur battery in the company aspects. Lithium sulfur battery or lithium ion battery. So in our case, we also make the lithium sulfur battery. So the lithium sulfur battery getting the higher energy density compared to lithium ion battery, therefore we are going. Even though when we are going for lithium sulfur battery, there is lot of issue during the lithium sulfur, the charging discharge process. You can see the charging discharge process, the lithium sulfide, the polysulfide formation is the big issue. So therefore the kinetics will be slowly, because the fast kinetics may be reduced after few cycles, charge discharge cycle. You can see the charging and the discharging cycle, yes. So therefore the people developing the highly stable material during the charge discharge process, like a volume expansion, or maybe it may be more stable material for getting the high energy density, power density. So when I make the single atom, I told you there is not a metal nanoparticle observed. We cannot able to see from the TEM analysis, only STM analysis we can see. So the graphene networks is highly spreaded by the vanadium single atom with the rhenium sulfides. You can see vanadium is separated very limited amount, yes, but in case of rhenium and sulfur, homogeneous distributed. So from this color mapping analysis, oxygen, nitrogen as well as carbon, you can see the high density, but in case of the vanadium is limited density, then we can say that vanadium single atom is bonded with the rhenium sulfide substrate of the graphitic carbon networks. So when we go for the vanadium single atoms compared to the metal nanoparticles, like metal nanosulfides, like vanadium rhenium sulfides, so I am going to prove the single atom behavior. So when I go for vanadium single atom, the blue one, you can see the anodic current density is higher and the cathodic also very high. So anodic density usually for the charging and the cathodic is the discharging. As when the cathodic will be higher, then the discharging will be high. Usually the battery need charging and the discharging will be very need high. Usually many batteries the charging very high and not symmetric, like discharging very fast. But in our case, it almost symmetric. It happens. But you can see there is anodic process for lithium Li2S6, how convert to Li2S, and again how retained after discharging process. So when I go for different candidates, the anodic peak and the cathodic peak also increase towards the positive and negative directions, and the durability also highly durable. After 2000 cycles, there is no much change for both the anodic as well as cathodic peaks, and the resistance. You can see the impedance analysis. This is RS value. This is the ion transportations. Usually this is the high frequency. This is low frequency. Is the low frequency from the ion transportations. This is the RCT value we calculate from the here. But in case of our optimal single atom decorated cartilage, going the lower RCT and the high ion transport behaviors. And so I also do the charge discharge process. You can see the specific capacity of our optimal cartilage is higher compared to the other cartilage, and the rate performance for different current density, it may be higher specific capacity and high reproducibility after higher current density. And you can see different current density when increasing the current density from 0.2 C coulomb to 5 coulomb, then the charging discharging almost retained, and durability for 600 cycles there is not much loss, and coulombic efficiency almost near to 99.95%. And we also do before and after cycling stability, but the before cycling there is only one semi circuits and another after cycles, because of the lithium polysulfide is absorbed by the surface modification. We also do some the partial for the commercial aspects, and we do the coulombic efficiency with the different charging in the full cell devices. So from the studies we told that the higher energy density and cycling stability and may be helpful for the future energy aspects like energy storage devices. And single atom cartilage, how it will use for water splitting. So before going to water splitting, I am explaining why we need hydrogen fuels rather than already available gasolines, diesel, natural gases. So usually all different energy device like energy sources available, but when go for the energy sources towards the conversion, energy conversion, so energy conversion like a specific energy, the specific energy of hydrogen is very high. Even though internal combustion of the energy engine in the car, but other sources like a diesel or gasolines around 20 to 30%. When go for hydrogen fuel cells, maybe around 60%. Because there is a lot of hydrogen fuel cell car is available, even the Korea, they are using car as well as the heavy vehicles also. But they told that when you are using for kilometers, when using for hydrogen source, maybe kilometer by maybe 1 rupees or 2 rupees kilometer. But in case of the petrol or diesels, maybe around 100 or 120 rupees, yes. Therefore, they told that maybe the hydrogen fuels maybe reduce the cost and we can travel very long distance. And it may be more convenience because it is also challenging because when we are using gasoline or other diesel, other fuel source, maybe contaminate the environment like a carbon dioxide or carbon monoxide liberation, yes. But it may be more convenience and quiet. There is no noise and it may be clean source. There is no any pollution in the atmosphere and already used for different vehicles like advanced the country, but maybe small industry they are using and future they plan to use, even already they are already used for different type of electric vehicles, even the hydrogen aircraft also already they make by some countries, developed countries like Europe. So what is water splitting? So the students have to know what is water splitting. So usually the media may be athletic or little basic media. Then nowadays people are also developing the sea water splitting because sea water is commercial, is already available. Yes. Therefore, we are using the sea water as well as the acidic media because industrial may be liberating the water may be highly acidic in nature. Then when whatever the media, they have to split the waters. Yes. Then when the oxygen may be liberated by the ionic part and hydrogen liberated by the cathodic parts. When we apply some potential, then it may be splitted because splitted the waters and one side hydrogen evolution happen, another one side is oxygen evolution happens because the hydrogen evolution side is cathode, oxygen evolution side is anode. So what is the problem in the commercial aspect of our industrial in the water splitting technology? Because water splitting technology they are using platinum or iridium based catalyst, but the cost is very high and maybe scarcity also another issue because availability of the earth is very limited and you can see commercial platinum carbon has carbon support like amorphous carbon support. When they use it for the HER, you can see after few cycles the potential loss. Usually the lower potential is very good, but when the potential loss after few cycles, we cannot be able to use for the catalyst for the long-term usage in the industry. And in case of the OER also similar. When they use it for the long-term, then maybe potential may be shifted towards the positive and there is issue for iridium or ruthenium based oxides. So why it is happen? Usually when they go for the HER and OER, the commercial material, we need to fabricate with some binders, yes, because we cannot able to coat the material over the current collectors like nickel foam or carbon cloth or carbon papers. So we need to use the binder. That binder may be degrade during the long time, the durability test. Therefore, the material may be dissolved slowly, the performance will be lost because the potential will lost for both OER and HER. You can see there is the problem. So why we have to bring the material from here to here? Because the lower water potential always very good because the theoretical one is 1.23 voltage, the potential, but we need to bring from here to here. Then the scientists need to make the hierarchical structure as well as the highly potential material for the next generation water splitting technology. So we have developed a different type of single atom catalyst over the transition metal chalcogenides. Usually transition metal chalcogenides like a sulfide or selenide based material. So especially these chalcogenide materials usually used for the high conductive media. That conductive media helps us to anchor the single atoms. Previously I told carbon network supported single atom, but I am going to discuss about the highly hierarchical structure like a transition metal chalcogenide supported single atom. That single atom may be act as the active site for OER and HER to enhance the HER and OER performance with the highly durable catalyst. So we also engineered recently the catalyst. Usually I told you when go for high loading, the metal cluster formation happen, but we are doing successful surface engineering technology to make the single atom ruthenium. And ruthenium, why we are choosing? Because ruthenium is more stable in acidic media. Because two types of water spreading or water electrolytes available. One is AEM, because anion exchange membrane water electrolyzer. Another one is proton exchange water electrolyzers. Compared to anion exchange water electrolyzers, proton exchange water electrolyzers is very difficult jobs because acidic media. Because acidic media stability is very limited in the first row transition material. Therefore, I am choosing second row or third row transition material like a ruthenium. But another question also you people raised, why you choose ruthenium? Because high cost material, but compared to iridium, 7 times lower than iridium cost. And another thing, I am using very limited percentage, like a 2%. I am not using more than 80% or 90%, but I am using single atom like a 2% or 3%. Therefore, very limited percentage I am using. Therefore, I am reducing the cost in different way. So when I make the material first, I make the cluster particles, because usually when my plan is going to make the high loading, I got the cluster particles. So interesting thing is I do some transformation via the new technology. So there is this material, maybe I am not still reported because we are aiming for some other big journals. So I transferred from the cluster to single atom. You can see there is highly transformed from the cluster to single atom. It's also proved by the Zan's analysis. You can see usually the cluster, the blue one, oxidation stage will be lower because close to maybe 1. But when going for the transformation of the cluster to single atom, the oxidation stage will be still increased. And you can see I told the blue one is cluster because majority of ruthenium bonded. But in case of our optimal catalyst, you can see there is not much bonded happen, only lower shift because below 2. Then I can claim that this may be bonded to the sulfur, there is not cluster formation because 100% is transformed from the cluster to single atom via this technology. So I also do the WTEXF analysis to prove or compare with the foil and our commercial catalyst, because this is below 2. You can see this is after 2 because the R value, and a similar observation I observed for the the ruthenium oxides and the cluster also. And when I go compare with the cluster and our single atom catalyst, you can see higher potential shift for the binding energy for ruthenium 3P and ruthenium 3D. Usually this is for carbon peaks, but 3D is close to the carbon. But other source like a substrate material, there is not much shift happens after modification, single atom transformation or before transformation. From the studies we can claim that the ruthenium is not doped. Thus ruthenium on the substrate is like a single atom modified with the substrate. So it may be another question. So I also do the HER performance when the blue one is cluster, and it may be boost the performance. It even compared to the platinum, it may be higher performances. And in case of the OER also, it may be increased high, lower potential. So the durability for more than 400 hours may be stable in both HER and OER, and overall water splitting. The commercial one showing 1.53 voltage because the voltage is very low when compared to the previous materials. So this may be 1.43, but there is not much reports. Still now they're struggling more than 1.49, but it's very difficult. But in case we are getting more than 1.43, but the durability for the overall water splitting also very high in acidic media. But previously I discussed about the basic media, but this is acidic media because I am going to use the proton exchange bottle electrolyzer. Yes. So another study also we developed the materials. That material we also analyzed. You can see copper with a different doping, behavior. But when the copper doped with the tungsten selenate substrate, so what is the changes happens? So how the selenium is changed, and different type of selenium, maybe one plus charge, another one is minus charge. Maybe one side is acted as a OER, another one is HER. And we also studied, and the 1T prime phase maintained even doping higher amount of copper. And we also do even 0.5 nanometer scale bar. You can see the homogeneous distributions. And we also do the structural investigations to prove the material, and do the HER and the kinetic studies and durability studies. And OER also we do in both comparative with the iridium oxide. You can see iridium oxides, the stability will be very big issue, but in our case maybe highly stable. And we also check the potential, over potential for both the OER and HER and OER. And after stability, because that is also one challenging, after durability for HER and OER, we also checked. Usually HER, there is no issue because the HER evolution reaction, HER is not damage the material, but OER damage lots because oxygen evolution is damaging, but our crystal may be retained after long-term durability. And we also do the theoretical calculations, and the closed delta G value is optimal calculation because a high loading 0.75 even compared to the other ratio is better. But in case of pure copper tungsten, highly anchored over because the hydrogen, and it may be not losing after evolution time. Therefore, the copper is not suitable. But in case of copper, high ratio with the tungsten is the better one, close to 0. But in other cases, we also do different pH. I told you different pH also very, but universal pH. I also do the different pH with the HER and OER, and this is the mechanism how oxygen absorption and desorption happens. And we also do the full cell devices and reversibility test. When comparing the commercial one, the reversibility is highly maintained for the oral water splittings, and the durability for more than 200 hours is more stable. And theoretical and experimental value also we tested with the different seconds, and it almost matched it. And the commercial aspect, we fabricate the AEM, anion exchange membrane water electrolyzers. It may be stable in both higher current density. So from the studies, we conclude that this is after stability test for oral water spreading, it highly retained the materials. There is not much loss happen for the element like a copper, tungsten or selenium. Usually the metal dissolution happen during the water spreading. So from the studies we conclude that our material may be more stable for both the OER and HER, and highly used for the anion exchange membrane water electrolyzer in the big cell 5 centimeter scale bar. Then maybe it used for the hydrogen production in industrial aspects. And we also studied a different type of material for overall water spreading, and there is a lot of reports we published today. And I am going to finally discuss about the energy storage devices like the supercapacitors, because different type of energy storage. Previously I told battery, but I am going to discuss about the supercapacitors. First, we are fabricating the materials because long time back, maybe 2016, around 2016, we fabricating the material like a metal nanoparticle with the graphite substrate. So after, when we are thinking this material, we need to fabricate with a nickel foam or other carbon substrate, we need some binder, yes. Then we are fabricating different type of material with a carbon substrate. That material has some issue, therefore we move to grow the active material over the nickel foam. You can see we are fabricating the materials like a oxide, then move to sulfide and move to selenide. Why move to sulfide to selenide? Because sulfide, compared to sulfide, selenide has high porosity because selenide size is very high. Then porosity will be enhanced. Therefore, electroactive sites increased, and finally energy density, power density also increased. Then when we go for commercial aspect like flexibility, then nickel foam also has some issue because nickel foam we cannot be able to bend more time, it will be break. Therefore, we moved from the nickel foam to the carbon cloth. You can see the carbon cloth, and we directly grow the material over the carbon cloth. That material may be used for the highly flexible energy storage device, both positive electrode and negative electrodes. And finally, we get the high energy density and power density from our flexible energy storage devices. We also developed a first sulfide based material for the flexible, and the selenide and phosphide and some telluride based materials. You can see some strategy usually making the metal nitride, they need the ammonia gas, but in our case we make without ammonia gas because ammonia annealing process may be hazardous to the environment. Therefore, we do some interesting things to without ammonia pyrolysis. We make the metal nitride in the core shell, and finally we tested with a different bending and flexible devices, and we also achieve the high energy density and power density. And we also do some material grown over the carbon cloth because carbon is a direct cloth, and we make the cloth with the conductivity because nickel plating or some copper plating. After that, we grow the material, and finally we have used it. And this is also one of our studies, highly flexible energy storage devices. And zinc ion battery, because zinc ion battery is similar to the supercapacitors. So we have fabricated the material and we have used zinc ion battery. Why we are moving from supercapacitor to zinc ion battery? Because the potential is very important. Maybe because you can see the potential, the running potential is very important because the potential very high, then we can go for, because directly proportional to the energy density. But in case of supercapacitor, we cannot be able to go for 1.6. After 1.6, the water splitting will happen. But in case of zinc ion battery, we can achieve around 2.1 or 2.2. But when go for 2.2, the energy density and power density is very high, even compared to the commercial available materials. So we also do the zinc ion battery with different bending. You can see the photo with the different bending and rate capability and durability. And we also check with the aqueous media and quasi-solid state like a flexible energy storage device. Usually the quasi-solid state has the higher resistance because of the ion transportation very bit slow compared to the liquid. But even though it may be highly bendable and twistable, and it may be used for the commercial applications. So this is our research group. So Professor Sang-Woo Kim, he is one of the leading professor in the Korea, as well as top 2 scientists, top 20%. I'm not telling top 2 scientists because there is many people nowadays they put top 2 world scientists, but I'm telling top 20 people in the world because he is the one pioneer for single graph inverter, single crystal graphene inverter, and you can see I am working as a research assistant professor because I have completed Ph.D. from India Anna University, and after that I moved here as a research assistant professor. This is our research groups like Ph.D. students and many master students. So this is our campus, and we have different groups because usually the graphene team and the PCP teams and the catalyst team, and this is our overall groups. You can see here I am, and the KAIST, this is well-known institute. You can see this is the photograph of KAIST different places, and the KAIST is top 1 university in Korea because the Korea around 300 universities because very small country, even it is similar to like a Tamil Nadu, the size, but the KAIST is, it has 300 university, but out of 300, it is number 1. University, the world rank university is around 13 to 16 for around 8 years because last consecutive 8 years, 9 years, below 20 ranking, QS ranking. So this one is top university, and you can see the video.
Determination. We are determined to pursue the highest goals. The Terman Report predicted the global emergence of KAIST 30 years ago, even before KAIST was created. A firm belief and commitment to developing ideas contributed to today's KAIST. We have worked hard to address the problems faced by Korea. The first Korean satellites that were made by KAIST are now known through the world. The first humanoid robot in Korea, Cubo, emerged as top global technology. Now, based on these achievements, we are moving forward toward new challenges to make the world.
Thank you. Maybe if some students need to enter the KAIST, maybe usually KAIST they see the top rank university, previous university is top maybe 100 universities whoever completed master degree or maybe whoever completed bachelor degree, because when you want to come inside the KAIST, you need to graduate from the top 100 university or top 200 university, one criteria. Another criteria is the possibility you have to publish paper in master degree or bachelor degree itself. That paper should be high reputed journals around maybe more than 10 impact factors. Then maybe possibility, because you can see I told previously the students you see in our laboratory, not only my laboratory, around 99% students from Korea only, or maybe 1 or 2 people or few people from US or Europe country. Indian students difficult to enter here. But the case, because India is not much, ranked university as India. But my suggestion, if you people need to or interested to join, please feel free to apply. But with some publications, reputed publications, it may be easier to enter. This is my suggestions. Maybe like a postdoc or research professors, maybe if you need some with a strong record of your profile, maybe very easier way to enter the KAIST. That's all maybe. So thank you for your kind attentions. So if you need any, if you have any questions, feel free to ask me. Or maybe I'm going for very fast in the last few sessions because maybe I feel that maybe you feel boring. That's why I go very fast. If you have any doubts or if you want to repeat, I can repeat or explain in very details. Thank you. Thank you so much.
Thank you, sir. Now we'll have query session. Thank you, sir, for sharing your insights and expertise with us today. Your lecture has been truly insightful. Thank you, sir. Sir, can we wind up the session?
Yes, ma'am.
Can we wind up the session?
Yes, ma'am. Okay, ma'am. Sure.
Thank you, sir.
Thank you, ma'am. Thank you for giving the great opportunity. So special thanks to Professor Girija, ma'am. And maybe one of my known persons, Babu, Dr. Babu, he is from Taiwan. He only told about this conference. So thank you for everyone. So thank you for your valuable time. Okay, thank you. Anybody have questions, please feel free to message me or mail me. Thank you so much.
Thank you, sir.
Thank you, ma'am. Bye, ma'am.
Good afternoon, all. If your actions inspire others to dream more, learn more, do more, and become more, you are a leader. Esteemed guests, participants, and faculty members, we have now reached the final and most significant part of our event, the valedictory session. It has been an incredible journey over the past 2 days, filled with insightful discussions, inspiring speeches, and valuable learning. We are honored to have Dr. K. Kalimuthu, Dean Research and Development, Dr.N.G.P. Arts and Science College, to deliver the valedictory address.
So respected head of the Department of Physics, and staff members from Department of Physics, and the scholars and students from other colleges and our own college. Good evening, one and all. Really, I am very happy to be here in this international conference and this one valedictory session. I really am very happy. And this type of conferences are need of the hour. Really, it's very difficult to organize a conference. So apart our staff members, they are taking keen interest in organizing such a type of international conferences. So apart from regular work, they concentrated more on this conference. So it's very difficult to arrange such a conferences. And in those days, no such conferences are needed, but nowadays it is very, very essential. So the students, I request the students to attend more such conferences, and also thank the organizers for organizing such a wonderful conference, and both online and offline mode. And the resource persons also, I think, it must be very useful for the audience. And also I request department staff members to organize more such type of programs, also hands-on training, etc., for the benefit of the students. So nowadays the theoretical part is necessary, but not much more. So the students and scholars, they need lots of hands-on training and this type of conferences, and this type of conferences leads to more interaction between various persons. So we can interact with foreign staff members or foreign professors, and very well you can exchange your ideas, and you will get some ideas from them, and also you can use that idea in your project, etc., etc. So this type of conferences are needed, and I congratulate all the organizers and coordinators and also head of the department for organizing such a very good international conference. And I think many members from various colleges participated in this, and with this I thank the organizers for giving me the opportunity. Thank you very much.
Thank you, sir. Now, we are excited to move on to a highlight of our program, the prize distribution session. This is a moment to celebrate the hard work, dedication, and achievements of our participation. I invite Dr. Kalimuthu, sir, Dean, Research and Development, to join us to facilitate the distribution of prizes. I would like to invite the winner of the third prize for oral prize winners. Let's give a warm round of applause for Vincent Raj from Tyagaraja College, Madurai. The second prize goes to Devi A from Dr.N.G.P Arts and Science College. And the first prize goes to Glory Renita from CIT Coimbatore. Prize winners are requested to report at the MC desk. Next, best oral presentation. Nivas Khanna from National College, Trichy, Annie from CIT Coimbatore, and P. Valarmadi from Gobi Arts College. Next, I would like to invite the winners of the poster presentation. Third prize goes to Dr.N.G.P from PSG College of Arts and Science, Coimbatore. The second prize goes to M.S. Basma Fatima from Hindustan University. And the first prize goes to Aishwarya P from National College, Trichy. Best Poster Presentation Award goes to Akshay Venkat V from Ratinam College. Thank you, sir.